Welcome, friend. Tonight, we're going on a journey into the invisible universe, the realm of dark matter. That mysterious substance that makes up most of everything, yet touches nothing we can see. Let your body settle into comfort. Let your breathing slow. There's nowhere you need to be, nothing you need to do. Just listen, and let these cosmic secrets wash over you like gentle waves. If you're finding peace in this moment, consider leaving a like and subscribe to join us on more journeys through the sleeping cosmos. We have so many mysteries to explore together, so many wonders waiting in the darkness. The universe you see is a lie, not a cruel deception, but a beautiful incompleteness. Everything visibly, every star burning in the night, every planet orbiting in the black, every galaxy spinning in the cosmic web, even your own body, made of atoms, all of it, represents just 15% of what exists. The rest is shadow. The rest is dark matter. Let's begin our descent into this invisible ocean. 5 times more dark matter exists than normal matter. For every atom in your body, every particle of light, every bit of substance you've ever touched, there are 5 phantom particles passing through you right now, utterly invisible, completely intangible. They're streaming through your bedroom, through the earth beneath you, through the very core of the planet, emerging on the other side without slowing down. You are bathed in darkness. This invisible substance forms a cosmic scaffolding. Dark matter creates the architecture upon which all visible matter hangs, like spider silk holding dewdrops at dawn. Without it, galaxies couldn't exist. The stars you see at night would never have formed. You wouldn't be here. None of us would. But here's the maddening part. We have no idea what dark matter actually is. We know it's there. We can measure its gravitational pull, watch it bend light from distant stars, see its fingerprints in the motion of galaxies. But we cannot see it, cannot touch it, cannot capture even a single particle in our most sensitive detectors. It is the greatest mystery in modern physics, a substance that dominates the universe, yet remains completely hidden. Scientists call this the dark matter problem, but perhaps it's not a problem at all. Perhaps it's an invitation to wonder. Dark matter doesn't emit light. It doesn't absorb light. It doesn't reflect light. Photons, particles of light, pass through dark matter as if it doesn't exist. Imagine a ghost so ghostly that even other ghosts don't notice it. Dark matter interacts with normal matter through gravity alone, the weakest force in nature. It's like trying to hear a whisper in a thunderstorm. Yet this whisper shapes everything. The Milky Way galaxy swims in a dark matter halo 10 times larger than the visible disk. Our home galaxy, 100,000 light-years of stars and nebulae and stellar nurseries, sits inside an invisible sphere 1,000,000 light-years across. This dark halo weighs more than 1,000,000,000,000 suns, yet remains completely unseen. We live inside the belly of an invisible whale. Every galaxy wears a similar shroud. The beautiful spirals captured by telescopes, those gorgeous pinwheels of light spanning hundreds of thousands of light years, are merely the bright centers of much larger structures. The visible parts of galaxies are like campfires in a vast, dark forest, tiny illuminated pockets in an ocean of shadow. Spiral galaxies shouldn't exist without dark matter. The mathematics is clear. Based on the visible matter alone, these cosmic pinwheels should spin themselves apart. The outer stars orbit so quickly that they should fling themselves into intergalactic space, like children flying off a too-fast merry-go-round. But they don't. Dark matter's gravity holds them in place, an invisible hand steadying the cosmic dance. Vera Rubin discovered this in the 1970s. She measured the rotation, speeds of spiral galaxies, and found something impossible. Stars at the galaxy's edge moved just as fast as stars near the center. This violated everything astronomers understood about orbital mechanics. The outer stars should have moved much slower, like Neptune lumbering around the sun while Mercury races, but they didn't. There was only one explanation: invisible mass, huge amounts of it, distributed throughout and around each galaxy. The dark matter halo's gravity was keeping everything together, like an enormous, unseen hand holding the stars in their paths. Rubin's discovery was initially dismissed, then debated, and finally accepted. She revolutionized astronomy by proving that most of the universe is missing. Or rather, that we were missing most of the universe. Fritz Zwicky predicted dark matter even earlier. In 1933, he studied the Coma Cluster, a congregation of more than 1,000 galaxies bound together by gravity. When he measured how fast these galaxies moved, he found they zipped around at speeds that should have torn the cluster apart billions of years ago. The visible matter couldn't provide enough gravity to hold the cluster together. Zwicky calculated that the cluster needed 400 times more mass than he could see. He called this missing mass Dunkel Materie, dark matter. His colleagues thought he was wrong. They thought his calculations were flawed, his observations mistaken. It took 40 years for the astronomical community to realize Zwicky was right. The universe is mostly made of something we cannot see. Dark matter forms vast cosmic webs between galaxy clusters. Strands of dark matter stretch across millions of light-years, creating a three-dimensional network like neural pathways in a vast brain. Galaxies form where these strands intersect, like lights along an invisible highway. This cosmic web is the largest structure in the universe, and it's made primarily of darkness. Scientists map this web using gravitational lensing. When light from distant galaxies passes through regions of dark matter, the gravity bends the light, creating distortions like looking through old window glass. By studying these distortions, astronomers can map where dark matter concentrates, even though they can't see it directly. It's like detecting an invisible hand by watching the ripples it makes in a pond. These maps reveal something breathtaking. The universe looks like a brain. The dark matter web resembles neural networks, with dense nodes connected by delicate filaments. Perhaps consciousness and cosmos follow the same architectural principles. Perhaps structure itself, at the largest and smallest scales, obeys the same hidden mathematics. But we're getting ahead of ourselves. Let's return to simpler mysteries. Dark matter particles pass through you constantly. Right now, millions, perhaps billions of dark matter particles are streaming through your body every second. They pass through your skin, your bones, your DNA, your very atoms, without touching anything. They emerge on the other side unchanged, like sunlight through a window, continuing their eternal journey through the cosmos. You cannot feel them. You will never feel them. They're interacting with you only through the weakest gravitational nudges, forces so tiny they're impossible to detect. You are transparent to dark matter, and dark matter is transparent to you. Two universes occupying the same space, never touching. Deep underground, physicists wait in the darkness, in abandoned mines and caverns, shielded from cosmic rays by miles of rock. Scientists have built the most sensitive detectors ever created. They're hunting for dark matter particles, hoping to catch just one collision between a dark matter particle and a normal atom. The detectors sit in pools of ultra-pure water, cooled to near absolute zero, monitored by thousands of sensors. They wait in perfect stillness, recording every tiny fluctuation, searching for the faint signature of dark matter. They've been waiting for decades. They've seen nothing certain yet. This silence tells its own story. Whatever dark matter is, it interacts with normal matter so rarely that we might go centuries without detecting it. Or perhaps we've already detected it and can't tell the signal from the noise. The uncertainty is maddening. It's also wonderful. Dark matter might be made of WIMPs. These are weakly interacting massive particles, theoretical particles that have mass but barely interact with anything else. WIMPs would pass through normal matter, like ghosts through walls, interacting only occasionally through the weak nuclear force and gravity. Scientists have been searching for WIMPs for 40 years without success. The lack of detection doesn't mean WIMPs don't exist. It might mean they're even more elusive than we thought. Or it might mean we're looking in the wrong place, at the wrong energies, with the wrong methods. Hunting dark matter is like trying to catch a whisper in a hurricane while wearing earplugs. Some scientists propose dark matter is made of ixions. These are much lighter than WIMPs, nearly massless, in fact, but they could exist in enormous numbers. Trillions upon trillions of ixions might be passing through every square centimeter of space each second. Their combined mass accounting for dark matter's gravitational effects. Ixions are named after a laundry detergent because they clean up certain problems in particle physics. This delightfully mundane naming convention in frontier physics reminds us that even the deepest mysteries are explored by humans with senses of humor. Other theories suggest dark matter is made of sterile neutrinos, primordial black holes, or particles we haven't even imagined yet. The truth is, we're fishing in the dark, hoping something bites, not knowing what we're trying to catch. This uncertainty is uncomfortable for science. We're accustomed to progress, 2 questions answered, 2 mysteries solved. But dark matter has resisted solution for 90 years. It challenges our methods, our instruments, our very ability to understand the universe. And perhaps that's its greatest gift. Dark matter shapes the cosmic microwave background. This ancient light, released 380,000 years after the Big Bang, carries an imprint of the early universe's structure. Tiny temperature fluctuations in this radiation variations of just millionths of a degree reveal where dark matter had already begun clumping together, creating the gravitational seeds that would eventually grow into galaxies. Without dark matter, these seeds wouldn't have formed quickly enough. Normal matter alone couldn't have collapsed fast enough to create the structures we see today. The universe needed dark matter's gravitational head start, its invisible scaffolding assembled in the cosmos's first moments. By studying these ancient patterns, scientists confirmed that dark matter must exist and must have been present since the universe's birth. This isn't speculation or theoretical convenience, it's written in the oldest light we can observe, a cosmic receipt from the universe's infancy. The Bullet Cluster proves dark matter exists. This system of colliding galaxy clusters provides smoking gun evidence for dark matter's reality. When 2 clusters smashed together at millions of miles per hour, the hot gas between the galaxies collided and slowed down, creating a visible shockwave. But most of the mass detected through gravitational lensing kept moving right through the collision. This separated mass is dark matter. It passed through the collision like 2 clouds of fog passing through each other, unaffected by the carnage happening to the normal matter. The bullet cluster shows us dark matter in action, its ghostly nature caught in the act of ignoring a cosmic catastrophe. This observation eliminates alternative theories that tried to explain galactic rotation curves without invoking new particles. Modified gravity theories predict that mass and gravity should stay together. But in the bullet cluster, most of the gravity is separated from most of the visible mass. Something invisible must be there. Dark matter creates Einstein rings. When a massive dark matter structure lies between Earth and a distant galaxy, the dark matter's gravity bends light from that background galaxy around it, creating circular or arc-shaped distortions. These rings and arcs are some of the most beautiful phenomena in astronomy: sculptures made of twisted light, artwork created by invisible artists. By studying these gravitational lenses, astronomers can weigh the invisible. They can measure how much dark matter exists in a given region by how much it bends background light. It's like deducing someone's weight by how much their footprints compress the sand, even though you never see the person. Some dark matter structures create multiple images of the same background galaxy. The light takes different paths around the dark matter lens, arriving at Earth from slightly different directions, creating a cosmic hall of mirrors. Astronomers have found cases where a single distant quasar appears 4 or even 8 times in the same image, each appearance showing the quasar at a slightly different moment in time. This means we can watch cosmic history out of order. The different light paths have different lengths, so light that left the quasar at different times arrives at Earth simultaneously. We might see the quasar first brighten, then dim, then brighten again in an order that makes no sense, since till we remember we're watching it reflected in dark matter's gravitational mirror. Dark matter particles might be their own antiparticles. Some theories suggest dark matter could annihilate with itself when two particles collide, releasing energy in the form of normal particles that we might detect. Scientists search for these annihilation signals in the cosmos, looking for excess gamma rays or other particles coming from dark matter-rich regions. So far, they've found tantalizing hints, but nothing conclusive. A possible signal from the galactic center made headlines, then faded under scrutiny. An anomaly in cosmic ray data suggested dark matter detection. Then other explanations emerged. The universe keeps teasing us with possibilities, then withholding confirmation. This dance between hope and disappointment is the rhythm of frontier science. Every anomaly might be the discovery of the century, or just a statistical fluctuation. Every signal might be dark matter finally revealing itself, or just background noise we didn't account for. The uncertainty is exhausting. It's also exhilarating. The local group swims in dark matter, our cosmic neighborhood containing the Milky Way, Andromeda, and about 50 smaller galaxies, a dark matter structure spanning 10 million light-years. This invisible architecture determines the motion of every galaxy in our local universe, orchestrating a slow gravitational dance that will eventually bring Andromeda and the Milky Way together in cosmic collision. That collision will happen in about 4 billion years. Don't worry, the distances between stars are so vast that our sun and its planets will almost certainly pass through the merger unscathed. But the night sky will be spectacular as 2 galaxies worth of stars mix and mingle overhead, their dark matter halos merging into a single, larger shroud. Even in collision, dark matter remains serene. While stars might be flung onto wild new orbits and gas clouds compress to birth millions of new stars, the dark matter halos will pass through each other almost unchanged, like two clouds of fog merging without turbulence. Darkness meets darkness without conflict. The cold, dark matter model successfully predicts cosmic structure. Simulations based on cold, dark matter particles moving slowly compared to light speed accurately reproduce the universe we observe. The cosmic web, galaxy clusters, the distribution of large-scale structure. This agreement between prediction and observation is remarkable. But the model fails at small scales. It predicts far more small satellite galaxies around large ones than we actually observe. It predicts dark matter should clump more densely at galaxy centers than observations suggest. These discrepancies are called the missing satellites problem and the cuspy halo problem. Maybe our observations are incomplete. Perhaps many small, faint galaxies remain undiscovered. Maybe normal matter physics is more complex than we thought, with stellar explosions and black holes redistributing dark matter in ways we haven't modeled. Or maybe dark matter isn't quite as simple as cold and weakly interacting. Maybe it has hidden complexities we haven't imagined. Warm dark matter could solve these problems. If dark matter particles moved faster in the early universe, warm rather than cold, small-scale structures wouldn't form as easily. This would naturally explain why we don't see as many small satellite galaxies as cold dark matter predicts. But warm dark matter creates its own problems, failing to match observations at larger scales. The universe, it seems, wants contradictory things. It needs dark matter to be cold enough to form large structures, but warm enough to avoid overforming small ones. Finding this balance might require dark matter to have properties we haven't considered, interactions we haven't modeled, behaviors we haven't imagined. Or perhaps dark matter isn't a single thing. Perhaps multiple types of dark matter exist, each with different properties, working together to create the universe we observe. Normal matter comes in dozens of varieties: quarks, leptons, bosons, all with different masses and interactions. Why should dark matter be simpler? Self-interacting dark matter is another possibility. What if dark matter particles can interact with each other, even though they don't interact with normal matter? This would create dark matter pressure that resists compression, naturally flattening the centers of dark matter halos and potentially solving the cuspy halo problem. Some models propose dark matter has its own force carriers, creating a dark sector of physics as complex as our own. There might be dark photons carrying dark electromagnetic forces between dark matter particles. There might even be dark atoms, dark chemistry, dark molecular clouds, an entire invisible universe sharing space with ours, as complex and rich as everything we can see, forever beyond our reach. This idea is both thrilling and troubling. Thrilling because it suggests reality is far richer than we imagined. Troubling because, if true, we might never understand it fully. An entire universe of complexity, forever invisible, forever unknowable. But let's not get lost in speculation. Let's return to what we can measure, what we can observe, what we know. Dark matter affects starlight in measurable ways. When astronomers measure the speed of stars orbiting a galaxy's center, they're sampling the gravitational field at that location. More distant stars should orbit more slowly, like planets in our solar system, but they don't. The rotation curves stay flat far beyond the visible edge of galaxies. This flat rotation curve is dark matter's clearest signature. It appears in spiral galaxies across the universe, from small dwarf irregulars to massive spiral giants. It's one of the most robust observations in astronomy, replicated thousands of times, undeniable in its consistency. Some alternative theories try to explain this without dark matter. Modified Newtonian dynamics. Mond suggests gravity behaves differently at low excitation, naturally producing flat rotation curves without requiring invisible mass. Mond matches galactic observations remarkably well, sometimes better than dark matter models. But Mond fails at larger scales. It can't explain the bullet cluster, can't account for gravitational lensing observations, can't reproduce the cosmic microwave backgrounds patterns. MOND works beautifully for individual galaxies, but collapses when confronted with the broader universe. It's a local solution to a cosmic problem. This doesn't necessarily mean Mond is wrong. Perhaps it's incomplete, capturing part of the truth but missing other pieces. Perhaps both modified gravity and dark matter are needed, working together in ways we haven't understood. Science isn't always about choosing between competing ideas. Sometimes it's about synthesizing them into something larger. Dark matter dominated the early universe. In the first 50,000 years after the Big Bang, dark matter's gravity was already sculpting structure, while normal matter remained too hot and chaotic to clump. These dark matter seeds grew over hundreds of millions of years, creating gravitational wells that eventually trapped normal matter, allowing the first stars and galaxies to form. Without dark matter's head start, the universe would still be a nearly uniform fog of hydrogen and helium. Structure formation would have happened too slowly. We'd still be waiting for the first galaxies to appear. The universe would be dark, not because of dark matter, but because there would be no stars yet to light it. So, in a strange way, dark matter makes the universe bright. This invisible substance created the scaffolding that allowed visible matter to shine. Darkness birthed light. The smallest galaxies are almost entirely dark matter. Dwarf spheroidal galaxies' tiny collections of a few million stars contain hundreds of times more dark matter than visible matter. They're like icebergs, where the tip represents 1% and the rest hides below. These dim, ghostly objects are the most dark matter-dominated structures we've ever found. One such galaxy, Segway 1, might hold the record. This ultrafaint dwarf orbits the Milky Way like a cosmic whisper, containing only about 1,000 stars, bright enough to detect. Yet it weighs as much as 1,000,000 suns. The dark matter outweighs the stars by a factor of 1,000 to 1. It's less a galaxy of stars than a cloud of darkness with a few lights scattered through it. Why don't these dark matter clumps accumulate more stars? Scientists still debate this question. Perhaps intense radiation from the first generations of stars blew the normal matter away, leaving only dark matter behind. Perhaps these structures formed in regions where normal matter was scarce. Or perhaps something about dark matter itself prevents star formation under certain conditions. These dark matter dominions offer unique laboratories because they contain so little normal matter. Complications from stellar physics and gas dynamics nearly disappear. Studying them is like studying dark matter in its purest form, uncontaminated by the messy behavior of atoms and stars. The Dragonfly 44 galaxy challenges our understanding. This ultra-diffused galaxy stretches across 60,000 light-years, nearly as wide as the Milky Way, but contains only 1% as many stars. It's like a galaxy rendered at low resolution, pixels missing, a shadow of what a galaxy should be. Yet it contains enough dark matter to weigh 1 trillion suns. If you could visit Dragonfly 44, the night sky would appear almost empty. Stars would be spaced so far apart that the closest neighboring sun might lie dozens of light-years away. It would be the loneliest place in the universe, a cosmic desert where darkness rules absolutely. How can such a structure exist? How can dark matter maintain a galaxy-sized halo with so few stars to light it? The galaxy is stable, held together by dark matter's gravity, persisting across billions of years. It shouldn't exist, yet there it floats, defying our models, expanding our ignorance. Some scientists suggest Dragonfly 44 formed normally but lost most of its stars to galactic encounters. Perhaps it passed too close to a larger galaxy, and tidal forces stripped away its stars while leaving the more diffuse dark matter halo intact. Others propose it formed in an unusual environment where star formation never got started properly. The truth is, we don't know. And finding more galaxies like Dragonfly 44, which was only discovered in 2016, might reveal whether it's an oddity or it represents a whole class of objects we've been missing. The universe might be full of ghost galaxies, invisible cities of darkness, waiting for us to learn how to see them. Dark matter halos rotate. Recent observations suggest that dark matter doesn't just sit in place, but spins along with the visible galaxy it surrounds. This rotation is slow, taking hundreds of millions of years to complete one turn, but it's measurable. It means dark matter isn't a static backdrop, but participates in the cosmic dance. This discovery complicates dark matter models. If dark matter interacts only through gravity, how does it acquire angular momentum? How does it know to spin in sync with the stars? The coordination suggests a connection between dark and normal matter stronger than we expected, a coupling we don't yet understand. Perhaps dark matter and normal matter exchange angular momentum during galaxy formation, their mutual gravity choreographing a shared rotation. Perhaps dark matter accumulated from smaller clumps that already had spin, their rotations adding up to produce the overall halo rotation. Or perhaps we're missing something fundamental about how dark matter behaves. The Milky Way's dark matter halo might contain streams and clumps. Computer simulations predict our galaxy's dark matter isn't smoothly distributed, but contains substructure rivers of dark matter flowing through the halo. Dense clumps orbiting like satellites, tidal debris from ancient galactic collisions. It's a turbulent sea, not a calm pool. These structures would be completely invisible, detectable only through their gravitational effects. If Earth passed through a dark matter stream, the local dark matter density would increase, potentially boosting signals in dark matter detectors. Scientists are now looking for such seasonal variations, hoping Earth's orbit carries us through regions of varying dark matter concentration. Imagine, we might swim through rivers of darkness, invisible currents flowing around and through us, changing with the seasons like cosmic tides. Right now, at this moment, you might be in a denser region of the dark matter sea, more particles passing through you than usual. Tomorrow, you might be in a void. There's no way to tell without detectors of extraordinary sensitivity. Dark matter might have temperature. Not temperature as we normally understand it. Dark matter doesn't radiate heat, but a measure of how fast dark matter particles move relative to each other. Cold dark matter moves slowly. Hot dark matter moves near light speed. Warm sits between these extremes. The universe's large-scale structure acts like a thermometer for dark matter. Hot dark matter would smooth out small structures, preventing small galaxies from forming. Cold dark matter allows structures at all scales. By observing what structures exist and which don't, astronomers constrain dark matter's temperature, measuring a property of particles we've never directly detected. Current observations suggest dark matter is cold, moving at speeds tiny compared to light. If dark matter particles have typical galactic velocities, around 200 kilometers per second, they're moving at less than 0.1% of light speed, slow enough to clump together under gravity, slow enough to create the universe we see. But cold is relative. Dark matter particles at 200 kilometers per second would cross Earth's diameter in a minute, circle the planet in 3.5 hours. They're slow on a cosmic scale, but blazingly fast by human standards. These are swift ghosts, streaming through your body at speeds that would tear any material object apart. Primordial black holes might be dark matter. What if, instead of exotic particles, dark matter consists of black holes formed in the universe's first moments? During the Big Bang's first second, density fluctuations might have collapsed directly into black holes, bypassing star formation entirely. These primordial black holes could have any mass from a grain of sand to thousands of suns. If dark matter is primordial black holes, they'd be scattered throughout the universe, invisible except through their gravity. They would pass through stars and planets like ghosts, creating no explosions, leaving no trails, interacting purely through gravitational pull. They'd be the perfect invisible mass. Several observations constrain this possibility. Very small primordial black holes would evaporate through Hawking radiation, so dark matter can't be too lightweight. Very large ones would create detectable gravitational lensing effects more often than observed. The sweet spot where primordial black holes could constitute dark matter without contradicting. Observations keep shrinking as our instruments improve. Recent gravitational wave detections have revived interest in this idea. LIGO has discovered black holes with unexpected masses, merging in unexpected ways. Could some be primordial? Could dark matter reveal itself, not through particle detectors, but through the ripples in spacetime created when primordial black holes collide? The question remains open. It's possible that some fraction of dark matter, perhaps 10%, perhaps none, consists of primordial black holes. The universe might employ multiple strategies for hiding its mass, using both exotic particles and ancient black holes to create the gravitational scaffolding of reality. Dark matter affects time. According to Einstein's general relativity, gravity slows time. Clocks run slightly slower on Earth's surface than at mountaintops because they're deeper in Earth's gravitational well. Dark matter, halos, containing enormous mass, create similar effects on cosmic scales. If you could somehow travel to a region of extremely dense dark matter, perhaps near the center of a galactic cluster, time would pass more slowly for you than for someone in intergalactic space. The effect would be tiny, perhaps a few microseconds per year, but it would be real. Dark matter doesn't just shape space, it shapes time itself. This means distant galaxies, seen through gravitational lenses, aren't just spatially distorted, but temporally distorted. light taking different paths through the dark matter arrives at different times, showing us the same event happening at staggered intervals. We're watching cosmic history reflected in a temporal hall of mirrors, where cause and effect can appear reversed. The universe is a single continuous space-time, but dark matter creates hills and valleys in that landscape. We live on Earth in a relatively shallow gravitational valley, experiencing time at a particular rate. Other civilizations elsewhere, if they exist, might experience time differently, aging faster or slower, depending on how deeply embedded they are in various gravitational wells. This is both humbling and beautiful. Time itself is not absolute, but flows like water, pooling in gravitational wells, rushing through empty space. Dark matter creates this landscape, invisible rivers cutting channels through the temporal terrain. Sterile neutrinos might compose dark matter. These hypothetical particles would be similar to regular neutrinos, but wouldn't interact through the weak nuclear force, hence sterile. They'd be heavier than normal neutrinos, but still quite light, and they'd exist in enormous numbers, their combined mass accounting for dark matter. Sterile neutrinos would solve several problems at once. They'd explain dark matter, while also explaining why regular neutrinos have mass a mystery in itself. They might decay very slowly, producing X-rays at specific energies that telescopes could detect. Scientists have searched for these signals and found tantalizing hints, including a mysterious X-ray line at 3.5 keV from galaxy clusters. But other explanations exist for these signals. The X-ray line might come from hot gas, not decaying dark matter. Every time astronomers find a potential dark matter signal, they must carefully rule out all normal astrophysical sources, a process that often takes years and usually results in disappointment. Still, the search continues. If sterile neutrinos are dark matter, they're decaying right now, releasing X-rays across the universe at a steady rate. We just need sensitive enough telescopes, looking at enough galaxies for enough time to separate the signal from the noise. Patience in science often measures in decades. Dark matter forms caustics. In regions where dark matter streams converge, the density can spike dramatically, creating fold structures called caustics. These are boundaries where dark matter's density becomes very large over a very short distance. Cosmic shock fronts in the dark matter sea. If Earth passed through such a caustic, our local dark matter density might spike by orders of magnitude for a brief period. Dark matter detectors might suddenly light up with signals. The effect would last only as long as Earth crossed the caustic, perhaps days or weeks, then fade back to background levels. Scientists have searched for such events in detector data, but haven't found clear evidence yet. This doesn't mean caustics don't exist. It might mean Earth hasn't encountered one during our brief period of observation. Or caustics might be smaller or less dense than models predict. The dark matter see's detailed structure remains unknown. Imagine you might walk through a dark matter caustic during your lifetime, a moment when the invisible substance around you suddenly concentrates. Millions more particles passing through your body than normal. You wouldn't feel anything. You wouldn't notice. But if instruments were watching, they might catch dark matter in the act of revealing itself. A brief window into the invisible. Galaxies without dark matter exist. In 2018, astronomers discovered NGC 1052d F20, a galaxy that appeared to contain little or no dark matter. This shocked the scientific community. If dark matter is fundamental to galaxy formation, how can a galaxy exist without it? The galaxy is real, enough about the size of the Milky Way, but with only 1% as many stars. Its stars move slowly, their velocities suggesting very little gravitating mass. Unlike every other galaxy observed, the visible matter seems to account for all the gravity. Dark matter is missing. Several explanations emerged. Perhaps the galaxy formed as part of a larger structure and had its dark matter stripped away by tidal interactions, like a moon losing its atmosphere. Perhaps it formed from material already lacking dark matter for mysterious reasons. Or perhaps the observations are wrong, the distance incorrectly measured, the velocities misinterpreted. Further study found more such galaxies. NGC 1052 DF4 appeared similar large, diffuse, apparently lacking dark matter. Either these are incredibly rare flukes, or a whole class of dark matter-deficient galaxies exists, hidden in our blind spots, waiting to complicate our theories. In a strange way, these galaxies strengthen the dark matter hypothesis. If dark matter and normal matter always appeared together, we might suspect they're actually the same thing. But finding them separated galaxies with dark matter but few stars, galaxies with stars but no dark matter, proves they're genuinely distinct. Normal and dark matter are different substances that happen to usually travel together but can be pulled apart. The cosmic web lights up in collisions. When dark matter filaments intersect, galaxies form at the junctions. When dark matter halos collide, the hot gas between galaxies heats even further, releasing X-rays. By mapping these X-ray emissions, astronomers can trace the cosmic web's structure, seeing dark matter's fingerprints glowing in high-energy light. The largest structures in the universe, the superclusters and voids, their existence to dark matter's gravitational action over billions of years. Dark matter flowed along the path of least resistance, accumulating in certain regions while evacuating others, creating the foamy cosmic structure we observe today. Voids, regions of space nearly empty of galaxies, aren't truly empty. They contain dark matter, just at lower density than average. They're like cosmic valleys, low-pressure regions in the dark matter atmosphere. Galaxies avoid them not because something repels galaxies, but because dark matter's relative absence means less gravity to collect normal matter. The largest known void, the Boats void, spans 330 million light-years. It's not completely empty. A few dozen galaxies huddle within it, lonely islands in a vast desert. But compared to typical cosmic regions, it's practically vacant. Flying through the Boats void, you might travel hundreds of millions of light-years before encountering the next galaxy cluster. Even in this void, dark matter exists. It's simply spread thinner, diluted across immense volumes. The void isn't absence, but deficiency. And that thinness itself is information, telling us how dark matter flowed in the early universe, where it drained away, where it accumulated. Dark matter might interact with itself through new forces. What if dark matter particles can scatter off each other, even though they don't interact with normal matter? This self-interacting dark matter would have pressure, resisting compression in galaxy centers, potentially solving the cuspy halo problem. Laboratory experiments can't test this directly. We'd need to collect dark matter particles and watch them interact with each other. Since we can't collect even one dark matter particle, studying billions of them is currently impossible. Instead, astronomers look for evidence in the shapes of dark matter halos. If dark matter self-interacts strongly, halo centers should be less dense than if it doesn't. Colliding galaxy clusters provide the best test. When clusters merge, their dark matter halos pass through each other. If dark matter self-interacts, the halos should show drag, slowing down slightly from internal collisions. If it doesn't interact, they should pass through cleanly. Current observations are ambiguous. Some clusters suggest weak self-interaction. Others show no evidence. The truth might lie in between. Dark matter might self-interact weakly, creating effects just at the edge of detectability. Or different types of dark matter might exist, some interacting, some not. The hunt for dark matter spans from underground mines to outer space. Terrestrial detectors sit deep underground, waiting for dark matter particles from the galaxy's halo to collide with their atoms. Space-based detectors search for the products of dark matter annihilation, looking for excess antimatter or gamma rays from dark matter-rich regions. Particle accelerators, like the Large Hadron Collider, try to create dark matter particles by smashing normal particles together at enormous energies. The idea, if dark matter particles exist, they should be producible at high enough energies. Scientists look for missing energy when particles collide and the output has less energy than the input. Something invisible might have carried that energy away. So far, every approach has yielded hints, anomalies, and suggestions, but no confirmed detection. Dark matter remains elusive across every search strategy. It's either extraordinarily shy or fundamentally different from what we're expecting. This multi-pronged approach is necessary. If one method succeeds, the others can confirm it. Finding dark matter in an underground detector, in collider experiments, and in astrophysical observations simultaneously would provide overwhelming evidence. Finding it through only one method invites skepticism. Could it be a mistake, an artifact, a misinterpretation? The Large Hadron Collider has searched for dark matter in countless collision events. When protons smash together at near light speed, they briefly create conditions similar to the early universe extreme temperatures and energies where exotic particles can spontaneously form. If dark matter particles can be created, this is one place it might happen. Detectors surround the collision points, tracking every particle that emerges. Sometimes energy appears to go missing. The combined energy of outgoing particles is less than what went in. This could indicate neutral, non-interacting particles like neutrinos escaped without detection. Or it could be dark matter created in the collision, passing through the detectors invisibly. Distinguishing these possibilities requires painstaking analysis. Scientists must account for every known particle, every possible interaction, every source of background noise. Only when all conventional explanations are exhausted can they cautiously suggest something new might be present. The LHC hasn't found definitive dark matter evidence yet, but it's constrained the possibilities, ruling out certain mass ranges and interaction strengths. With each year of operation, the allowed parameter space shrinks. Dark matter has fewer places to hide. The IceCube detector in Antarctica looks for dark matter in a different way. Buried in Antarctic ice, this detector searches for neutrinos from dark matter annihilation in the sun's core. Dark matter particles from the galactic halo constantly passed through the sun. Most pass through cleanly, but occasionally one scatters off a solar atom and loses energy, becoming gravitationally trapped. Over billions of years, dark matter accumulates in the sun's center. If dark matter particles are their own antiparticles, this accumulated dark matter should slowly annihilate, producing neutrinos that escape the sun and stream toward Earth. IceCube looks for these neutrinos, attempting to catch dark matter destroying itself inside our star. So far, IceCube has seen no clear signal. This limits how quickly dark matter can annihilate, constraining certain models. The Sun should contain a vast amount of accumulated dark matter by now. If it's annihilating, we should see it. The silence suggests either dark matter doesn't self-annihilate, or it does so more rarely than some theories predict. But absence of evidence isn't evidence of absence. Perhaps IceCube isn't sensitive enough yet. Perhaps we're looking at the wrong energies. Perhaps dark matter annihilation produces particles that decay before reaching Earth. The search continues, patient and methodical. Dark matter might decay. If dark matter particles are unstable, they should slowly fall apart over immense timescales, perhaps producing normal particles we can detect. The universe's age sets a lower limit. If dark matter decayed quickly, it would be gone by now, but it might decay slowly over timescales of trillions of years. A decaying dark matter particle might release a photon, a neutrino, or other particles. These decay products would appear throughout space, creating a diffuse glow at specific energies determined by the dark matter particle's mass. Telescopes scan the sky for such signals, searching for unexplained emission lines that could indicate dark matter decay. The 3.5 keV X-ray line mentioned earlier is one candidate, observed in galaxy clusters and the galactic center. This faint X-ray emission at a very specific energy doesn't match any known atomic transition. It could be dark matter particles decaying into photons, or it could be something mundane we haven't identified yet. Confirming dark matter decay would be revolutionary. It would give us a direct window into dark matter's properties, its mass, lifetime, decay channels. We could study dark matter through its death, learning about something we cannot touch by observing what it becomes when it falls apart. Dark matter makes up most of you. Well, not you specifically. Your atoms are normal matter, but most of the gravitational field that holds you to Earth. Most of the mass creating the solar system's gravitational environment. Most of the galaxy's binding force keeping our sun in orbit. All of that comes from dark matter. Your existence depends on dark matter's gravity. Without it, galaxies wouldn't have formed. Stars like the sun wouldn't exist. Planets wouldn't have coalesced. The atoms in your body, forged in earlier generations of stars, would still be scattered across intergalactic space as diffuse gas. In that sense, you're a child of darkness, not made from it, but possible because of it. Dark matter created the cosmic environment where life could arise, the gravitational architecture supporting stellar birth, planetary formation, chemical evolution, biological emergence. This invisible substance, which you'll never see or touch, is as fundamental to your existence as oxygen and water. It's woven into your origin story, a silent co-author of your biography. Dark matter's nature remains one of science's deepest mysteries. Nearly a century after Fritz Zwicky's first hint, after decades of increasingly sophisticated observations and experiments, after thousands of scientists dedicating careers to the search, we still don't know what it is. This is humbling. For all our telescopes and detectors, all our mathematics and theories, the universe holds its secrets close. 5 times more of reality is hidden than revealed, and we're still fumbling in the darkness, searching for something we cannot see. Yet there's beauty in this mystery. It reminds us how much remains unknown, how vast the undiscovered country stretches before us. Every answered question births new mysteries. Every solved puzzle reveals deeper enigmas waiting beneath. Dark matter is an invitation to wonder. It asks us to imagine substances we cannot perceive, to trust mathematics and observation even when they lead to uncomfortable conclusions, to remain humble before a cosmos that outstrips our understanding. As you drift toward sleep, let this sink in. You are surrounded by mystery, the space around you, the room you're in, your very body, all of it, permeated by invisible substance, dark matter particles streaming through you by the billions each second, forever intangible, forever hidden. You live in a universe mostly composed of something you'll never directly experience, and somehow that's perfect. That's exactly as it should be. The darkness is not absence, but presence. The invisible is not nothing, but something profound. Let that wonder cradle you as you sleep. Dark matter might have helped form the first stars. In the universe's infancy, before any stars existed, dark matter clumps pulled hydrogen and helium gas into dense pockets. These gas clouds collapsed under their own weight, heating up until nuclear fusion ignited, birthing the first generation of stars, massive, brilliant, and short-lived. Without dark matter's gravitational seeds, this process would have taken much longer. The universe might have remained dark for hundreds of millions of additional years, a lightless void waiting for gravity to slowly accomplish what dark matter achieved quickly. The first sunrise in cosmic history happened because darkness made it possible. For tons might sound like a lot, but dark matter is so weakly interacting that even this massive detector might go years without a clear signal. The experiment runs continuously, recording every tiny event, searching for the characteristic signature that would indicate dark matter rather than background radiation. Background radiation is the enemy. Cosmic rays, naturally radioactive materials in the detector components, radon gas seeping from rock coal, create signals that can mimic dark matter. Years of work go into eliminating these backgrounds, building the detector from the purest materials available, placing it deep underground where miles of rock shield it from cosmic rays. Despite these precautions, background signals still occur. Scientists must carefully analyze each event, using its energy, timing, and position to determine its likely source. Only events that can't be explained by any known background might be dark matter, and, even then, more evidence is needed before claiming discovery. This painstaking process has continued for decades across dozens of experiments. Each generation builds larger, purer, more sensitive detectors, pushing deeper into the parameter space where dark matter might hide. Each null result constrains the possibilities, telling us where dark matter isn't, even as we search for where it is. Dark matter helps galaxies survive. When massive stars explode as supernova, they release tremendous energy enough to blow gas out of small galaxies entirely, without dark matter's extra gravity holding things together. Many dwarf galaxies would have lost all their gas after just a few supernova-ending star formation forever. Dark matter's gravitational well is deep enough to retain gas even after violent explosions. This allows star formation to continue over billions of years, producing multiple generations of stars, enriching the gas with heavier elements, creating the chemical complexity that makes planets and life possible. In a universe without dark matter, dwarf galaxies would be sterile places. Few stars formed early, then nothing. The galaxy stripped of raw materials by its own stellar violence. The beautiful diversity of galaxy types we observe owes itself partly to dark matter. moderating stellar feedback and allowing galactic ecosystems to develop. This protective role extends to larger galaxies too. The Milky Way experiences supernova regularly, about 2 or 3 per century. Each explosion releases as much energy as the Sun will emit over its entire lifetime, all in a few seconds. Without dark matter's gravity steadying the galaxy, these explosions might gradually disperse our galaxy's gas, ending star formation prematurely. Instead, the gas remains bound, recycled, reformed into new stars. The cycle continues. Stars born, stars die, gas enriched, new stars formed from enriched gas. Dark matter enables this cosmic circle of life, invisible midwife to every stellar generation. You exist because dark matter protected the galaxy's gas long enough for the Sun to form, for Earth to coalesce, for life to arise and evolve. Your atoms were forged in stars that only existed because dark matter held their birthplace together. The chain of causation connecting you to dark matter is as real as the chain connecting you to your ancestors. Dark matter's gravitational lensing creates time delays. When light from a distant quasar passes through a massive galaxy cluster on its way to Earth, it can take multiple paths around the cluster's dark matter halo. These paths have different lengths, so light traveling them arrives at different times, sometimes separated by days, weeks, or even years. Astronomers use these time delays to measure the universe's expansion rate. By knowing the distance to the cluster and the time delay between multiple images of the same quasar, they can calculate the Hubble constant, the parameter describing how fast the universe expands. It's a beautiful example of using dark matter as a cosmic tool. Its very obscurity making possible measurements we couldn't achieve any other way. The measurements don't all agree. Time delay studies give one value for the Hubble constant. Observations of the cosmic microwave background give a different value. This discrepancy, called the Hubble tension, is one of the biggest puzzles in modern cosmology. Either our measurements have systematic errors, or something fundamental about the universe differs from our models. Could dark matter hold the key to resolving this tension? Perhaps dark matter's properties vary with time or space in ways we haven't accounted for. Perhaps dark matter interacts with dark energy more strongly than we thought. Perhaps the early universe contained additional components, early dark energy, or other exotic substances that affected the expansion history. These possibilities remain speculative, but the Hubble tension reminds us that dark matter exists within a larger web of cosmic mysteries. Understanding any one piece, dark matter, dark energy, cosmic expansion, structure, formation, requires understanding how all the pieces fit together. The universe is a puzzle where every piece affects every other. Let your mind drift with this interconnectedness. Nothing in the cosmos exists in isolation. Every particle influences every other through gravity's infinite reach. Dark matter shapes galaxies. Galaxies shape their surroundings. Those surroundings feed back on dark matter's distribution. It's loops within loops, causation forming circles, the universe bootstrapping itself into existence through self-consistent mathematics. This is deeper than physics. This is poetry written in the language of mathematics, where beauty and truth converge, where the abstract becomes concrete, where invisible influences create visible realities. Dark matter is part of this cosmic poem, an invisible verse without which the whole structure would collapse. As you settle deeper into rest, let this awareness wash over you. You're part of the poem too. Your body, made of star stuff, held by dark matter's invisible hand, conscious and wondering, participating in the universe's long journey of self-discovery. The cosmos peers at itself through your eyes, ponders its mysteries through your thoughts. This is what it means to be human in a universe of dark matter, to be a small eddy of awareness in an ocean of mystery, to recognize our ignorance and find joy in it, to seek understanding knowing we'll never achieve completeness. The journey matters more than the destination. The search itself is the discovery. Dark matter might explain the universe's geometry. Einstein's equations allow for 3 possible shapes of space: positively curved like a sphere, negatively curved like a saddle, or perfectly flat like a plane extending forever. Observations show our universe is almost perfectly flat, a cosmic knife edge between the other possibilities. This flatness requires a specific total energy density. Too much mass energy and space curves positively. Too little and it curves negatively. The amount of normal matter alone isn't enough to flatten space. Dark matter's additional mass brings us closer, and when combined with dark energy, the total reaches exactly the critical density needed for flatness. Why is the universe flat? This question haunts cosmologists. The flatness seems too perfect to be coincidence, yet we have no proven explanation for why space should have this particular geometry. Some invoke inflation, a period of exponential expansion in the universe's first fraction of a second, which would naturally flatten space, like stretching a balloon until its surface appears flat. But inflation itself remains unproven, a beautiful theory matching observations, but not yet confirmed by direct evidence. And even if inflation occurred, we'd still need to understand what caused it, what physics drove that explosive expansion. Questions nest inside questions, mysteries within mysteries. The geometry of space might sound abstract, but it determines the universe's fate. In a positively curved universe, expansion would eventually stop and reverse, everything collapsing back into a big crunch. In a negatively curved universe, expansion continues forever, space growing ever more empty and cold. In a flat universe, our universe, the expansion continues eternally, gradually slowing, but never quite stopping. Dark matter participates in this cosmic geometry. Its gravity helping determine how space curves, how the universe evolves, what ultimate fate awaits. Every dark matter particle contributes its tiny gravitational influence to the total. Billions upon billions of particles collectively shaping the architecture of reality itself. Axion dark matter would behave like a wave. Unlike WIMPs, which would act as discrete particles, Ixions, at the low masses most theories predict, would have wavelengths measured in kilometers, or even larger. A cloud of Ixions wouldn't be individual particles buzzing around, but a coherent wave, oscillating at a specific frequency determined by the Axion's mass. This wave nature changes how we search for Ixions. Instead of waiting for an individual particle collision, detectors look for the electromagnetic waves that Ixions should produce when passing through strong magnetic fields. The detector essentially becomes a radio receiver, tuned to frequencies corresponding to possible axion masses, listening for the whisper of dark matter, converting into electromagnetic radiation. These experiments require extraordinarily sensitive electronics and powerful magnets. Scientists must scan through billions of possible frequencies, spending time at each to see if a signal appears. It's like searching for a specific radio station when you don't know the frequency. Can't be sure the station exists, and the signal if present is weaker than any natural radio source. Several experiments worldwide pursue this strategy. A DMX in Washington, Haystack at Yale, ORGAN in Australia, listening to the cosmos at different frequencies, hoping Ixians will sing to them in whispers of electromagnetic radiation. So far, no confirmed detection, but each frequency ruled out narrows the search space, bringing us closer to either discovery or definitive exclusion. If Ixians exist, they're oscillating through you right now. Their wavelength might be larger than your body, meaning you'd be inside a single wave crest, experiencing the Axian field as a slowly changing background rather than individual particles. You wouldn't feel it, wouldn't notice it, but in a sense, you'd be breathing dark matter, swimming in its wave-like presence. The universe would be filled with these waves, dark matter rippling through space at frequencies imperceptible to human senses. It would be like living inside an ocean where the waves are measured in kilometers and take seconds or minutes to oscillate. Motion so slow and vast you'd never directly perceive it, yet it would be everywhere, always. Dark matter might explain cosmic rays. High-energy particles constantly bombard Earth from space protons, atomic nuclei, even heavier particles traveling at near light speed. Most come from supernova explosions and other violent cosmic events. But some cosmic rays have energies exceeding anything we can explain. Particles carrying as much energy as a well-thrown baseball compressed into a single atomic nucleus. Where do these ultra-high-energy cosmic rays originate? The most powerful particle accelerators in the universe colliding neutron stars, supermassive black holes, gamma-ray bursts still fall short of explaining the highest energies observed. Some physicists speculate that dark matter annihilation might contribute, with dark matter particles colliding and converting their mass into energetic particles that eventually reach Earth. This remains highly speculative. Most dark matter candidates wouldn't produce cosmic rays energetic enough to explain the observations, but more exotic dark matter models super-heavy particles, for instance, might decay or annihilate to produce the ultra-high-energy cosmic rays we observe. It's a long shot, but in dark matter research, long shots are sometimes all we have. Every few seconds, an ultra-high-energy cosmic ray strikes Earth's atmosphere, creating a cascade of secondary particles that rain down across hundreds of square kilometers. Arrays of detectors spread across remote locations, the Pierre Auger Observatory in Argentina, the Telescope Array in Utah watch for these cascades, measuring their energy and arrival direction, seeking patterns that might reveal their source. Most detected cosmic rays show no clear pattern, arriving from all directions as if their sources are scattered throughout the universe or their paths scrambled by magnetic fields. But occasionally, clusters appear multiple cosmic rays arriving from similar directions, hinting at a specific source. These clusters fuel hope that someday we'll trace cosmic rays back to their origin and understand what accelerates them to such extraordinary energies. Perhaps dark matter plays a role, perhaps not. The universe keeps its secrets, revealing them slowly, one careful observation at a time. Simulated universes test dark matter theories. Cosmologists create virtual universes inside supercomputers, starting from the conditions moments after the Big Bang and letting physics evolve forward billions of simulated years. These simulations can run with different dark matter properties, changing its mass, interaction strength, or temperature to see which versions produce universes resembling our own. The Illustris simulation, run in 2014, modeled a cubic region of space 350 million light-years on each side, tracking the evolution of both dark and normal matter across cosmic history. It successfully reproduced the cosmic web, galaxy clusters, individual galaxies with realistic properties. The simulation required 8,000 computer processors running continuously for months, a tremendous computational effort to create a universe in silicon. These simulations reveal dark matter's role in vivid detail. You can watch dark matter halos grow over time, small clumps merging into larger structures, filaments stretching between concentrations, voids expanding. You can see normal matter flowing along dark matter scaffolding, lighting up where dark matter is densest, revealing the invisible architecture through visible consequences. But simulations depend on assumptions. If we've misunderstood dark matter's properties, the simulations will produce universes unlike our own. When simulated and observed universes match as they increasingly do, it builds confidence that our dark matter models capture essential truth. When they diverge, it signals opportunities to refine our understanding. The missing satellite problem came from simulations' predictions that didn't match observations, forcing physicists to question whether dark matter physics is more complex than simple cold dark matter models assume. Similarly, the cuspy halo problem arose from simulations predicting denser galaxy centers than observations show. These discrepancies drive progress, highlighting where our knowledge remains incomplete. Dark matter's true nature might be testable in a laboratory. Some dark matter candidates, axions, for instance, could be produced in particle accelerators or created through laser experiments. By smashing particles together or creating extreme electromagnetic fields, physicists might generate dark matter particles on Earth, detecting them through their gravitational effects or rare interactions with normal matter. This would be the ultimate confirmation, creating dark matter ourselves, studying it under controlled conditions, measuring its properties directly rather than inferring them from astronomical observations. It would transform dark matter from cosmic mystery to laboratory science, from abstract theoretical entity to manipulable reality. But producing dark matter in detectable quantities might be impossible. If dark matter particles are very heavy or interact incredibly weakly, creating them would require energies beyond any conceivable accelerator. We might be permanently limited to observing dark matter in space, forever unable to capture and study it directly. This possibility doesn't diminish the value of searching. Even negative results constrain theories, eliminating wrong ideas and focusing attention on remaining possibilities. Science advances through both discovery and exclusion, through learning what is and what cannot be. The density of dark matter in your vicinity is about 0.3 protons per cubic centimeter. This sounds like almost nothing, and it is, by terrestrial standards. The best laboratory vacuums on Earth contain billions of particles per cubic centimeter. Even interstellar space between stars contains about 1 atom per cubic centimeter. Dark matter is diffuse beyond imagination. Yet, when summed over the entire Milky Way halosphere, 1 million light-years across this diffuse substance amounts to 1 trillion solar masses. It's the cosmic version of a little bit goes a long way, tiny local density, but so much volume that the total mass dominates. This diffuseness makes detection extraordinarily difficult. With only 0.3 dark matter particles per cubic centimeter passing through your body constantly, and each particle interacting so weakly that collisions are incredibly rare. Catching even one interaction requires enormous detectors running for years. It's like trying to catch raindrops in the desert, possible in principle, but requiring tremendous patience. Yet this same diffuseness ensures dark matter doesn't clump into dense, dangerous objects in our cosmic neighborhood. If dark matter could collapse under its own gravity the way normal matter does, we might have dark matter planets, dark matter stars, even dark matter black holes wandering through the galaxy. Instead, dark matter spreads itself smoothly, creating a gentle gravitational backdrop rather than concentrated threats. You're safer because dark matter is weak. Its inability to interact or clump protects you from its presence, letting you coexist with it peacefully, like two travelers sharing a road but never touching. Dark matter might have formed before normal matter. In the first microseconds after the Big Bang, the universe was too hot for protons and neutrons to exist. Quarks and gluons filled space in a plasma so energetic that stable particles couldn't form. But dark matter particles, if they don't interact through the strong nuclear force, might have formed earlier, condensing out of the primordial soup before normal matter did. This would make dark matter the universe's firstborn substance, predating everything we can see. Stars, planets, atoms, even the protons and neutrons comprising atoms all came later, after dark matter had already established its presence. The visible universe built itself on a foundation of prior darkness. Evidence for this comes from the cosmic microwave background. The patterns in that ancient light show dark matter was already clumping by the time the CMB was released, 380,000 years after the Big Bang. For dark matter to be clumped by then, it must have started forming structures, earlier perhaps, much earlier, in the universe's first moments. If confirmed, this sequence has philosophical weight. Darkness came first. Light emerged later, illuminating a universe already structured by invisible forces. The visible arose from the invisible, consciousness from matter, order from chaos, sequence of emergence, where each new level builds on the foundation of what came before. It's a creation story, written in physics, not competing with traditional creation myths, but complementing them, offering a scientific narrative of beginnings that carries its own sense of wonder and meaning. The coldest dark matter would move at centimeters per second. Theoretical models exist where dark matter particles are super ultra cold, barely moving at all on cosmic scales. Such dark matter would clump extremely efficiently, creating tiny lens structures far smaller than galaxies, potentially even planet-sized dark matter clumps wandering the galaxy. These ultra-compact dark matter objects would be completely invisible, but could be detected through gravitational lensing. If one passed between Earth and a distant star, the star would briefly brighten as the dark matter clump's gravity focuses its light toward us. An event called a microlensing event. Surveys monitor millions of stars, looking for these brightening. Several experiments have detected microlensing events, but most are explained by ordinary stars or brown dwarf stem objects between planets and stars in mass passing in front of background stars. A few events remain unexplained, possibly indicating dark matter clumps, but the evidence is far from conclusive. If supercold dark matter exists, these clumps might occasionally pass through the solar system, creating tiny gravitational perturbations. Some researchers have searched for anomalies in planetary orbits or spacecraft trajectories that might indicate dark matter clumps passing nearby. Nothing definitive has emerged, but the searches continue, patient and methodical. Dark matter astronomy is often a waiting game instruments, running continuously, eyes on the sky, hoping the universe reveals itself in a moment of cosmic serendipity. Discovery requires both preparation and luck, readiness to recognize the signal when it finally appears. Galaxies amplify dark matter's effects. When light passes near a massive galaxy, the galaxy's gravity dominated by its dark matter halo bends the light path. This gravitational lensing can magnify background objects, turning galaxies into natural telescopes that allow us to see distant objects otherwise too faint to detect. The Hubble Space Telescope has used galaxy clusters as lenses to observe some of the most distant galaxies ever seen. Objects so far away that their light has traveled for over 13 billion years. These glimpses of the early universe are only possible because dark matter in intervening clusters bends and brightens the light, making the invisible a tool for discovery. Gravitational lensing sometimes creates multiple images of the same background object, a cosmic funhouse mirror effect. A single quasar might appear 3 or 4 times in the same telescope image, each appearance showing the quasar at a slightly different time in its history because the light paths have different lengths. This time delay allows unique astronomical measurements. When the quasar brightens or dims, each image reflects that change at different times, separated by days to months. By measuring these delays and knowing the lensing geometry, astronomers can determine the Hubble constant independently, confirming or challenging other measurements of cosmic expansion. Dark matter becomes an astronomical instrument, a tool we didn't build but learned to use, extending our vision across the universe in ways impossible through technology alone. Nature provides what we cannot create if we're clever enough to recognize and exploit it. Warm dark matter might explain the Milky Way's structure. Our galaxy contains a flat disk of stars, a central bulge, and a spherical halo of old stars. The disk's thinness has always puzzled astronomers. Why didn't collisions and gravitational interactions puff it up over time? Perhaps warm dark matter's faster motion early in galactic history heated the disk less than cold dark matter would have, allowing it to remain thin. This is speculative, one of many attempts to explain galactic structures using dark matter properties we haven't confirmed. It illustrates how dark matter's nature affects every aspect of the universe we observe. Change dark matter's properties even slightly, and galaxies might look completely different: thicker disks, fewer satellites, altered rotation curves. The universe is finely tuned, each component playing a specific role in creating the cosmic symphony we observe. Remove dark matter, and the music stops. Change its properties, and the melody shifts. We live in one universe among infinite possibilities. Our particular cosmic arrangement, produced by the specific properties of dark matter and other fundamental components. Why these properties and not others? Why this particular dark matter rather than something else? These questions push beyond physics into metaphysics, touching on why anything exists rather than nothing. Why the universe is comprehensible rather than chaotic. Science answers how brilliantly. Why remains persistently elusive. But perhaps that's appropriate. Perhaps the universe isn't obligated to make sense to us, isn't designed for our understanding. Perhaps mystery is intrinsic, incompleteness unavoidable, and accepting this is part of wisdom, knowing what we can know while respecting what we cannot. Dark matter might interact with neutrinos, these ghostly particles produced copiously in the sun and in supernova explosions, barely interact with normal matter. Trillions pass through your body every second, most emerging from Earth's far side after traveling straight through the planet without stopping. If dark matter interacts with neutrinos more strongly than with other particles, neutrino detectors might indirectly detect dark matter. The idea is that dark matter particles in the galaxy could scatter neutrinos, changing their direction or energy in detectable ways. By studying neutrinos from the sun or from distant supernova, scientists might find anomalies indicating dark matter interaction. It's indirect detection, observing the messengers, rather than dark matter itself. But any confirmed signal would be revolutionary. Neutrino physics is already strange. These particles oscillate between three types as they travel, transforming from electron neutrinos to muon neutrinos to tau neutrinos in a quantum dance that still isn't fully understood. Adding dark matter to neutrino physics makes an already complex situation more intricate, but might explain anomalies that currently puzzle researchers. The universe seems designed, every answer revealing deeper questions. Dark matter intertwined with neutrinos, both barely interacting with ordinary matter, both produced in the universe's most violent events, both streaming through space in numbers beyond imagining. Two shadows dancing together, occasionally tangible, mostly invisible. Your body is transparent to neutrinos and dark matter alike. Both pass through you constantly, unseeable and unfelt, yet real as the ground beneath you, the air you breathe, the thoughts flowing through your mind. Invisible doesn't mean non-existent. Intangible doesn't mean unimportant. Dark matter might decay into photons. Some theoretical models predict dark matter particles slowly falling apart over immense timescales, each decay producing one or more photons, particles of light-hat, specific energies determined by the dark matter particle's mass. These photons would accumulate over cosmic history, creating a diffuse glow at particular wavelengths. Telescopes search for this glow, comparing observed cosmic backgrounds to predictions from known sources. Any excess light that can't be explained by stars, gas, dust, or other normal astrophysical objects might indicate decaying dark matter. The challenge is distinguishing signal from noise when the signal is expected to be incredibly faint and the noise from conventional sources is strong. Several claimed detections have appeared over the years, each generating excitement, followed by skeptical analysis. The 3.5 keV X-ray line mentioned earlier is one example, a signal observed in galaxy clusters that could be decaying dark matter or could be something mundane. Years after its initial detection, the debate continues, more data being gathered, alternative explanations being tested. This exemplifies dark matter research's difficulty. Even with the universe full of dark matter, detecting it is so challenging that signals remain ambiguous for years. Multiple independent observations are needed. Alternative explanations must be ruled out, and even then, the community remains cautious. The cost of false discovery is high-wasted effort, damaged credibility, misled theoretical work. Better to be patient than premature. Better to remain uncertain than falsely certain. This conservative approach frustrates those eager for breakthroughs but protects science's integrity, ensuring claims rest on solid evidence rather than wishful thinking. The Andromeda Galaxy's dark matter will merge with ours. In about 4 billion years, when the Milky Way and Andromeda collide, their dark matter halos will interpenetrate and eventually merge. The process will take hundreds of millions of years. Dark matter's diffuse nature, allowing gradual mixing rather than violent collision. During the merger, Earth and the solar system will likely survive intact. The distances between stars are so vast that stellar collisions are improbable even when galaxies merge. Our Sun might be flung onto a different orbit, carrying Earth and other planets along. But the solar system itself should remain gravitationally bound and stable. The night sky will transform Andromeda, currently a faint smudge visible from dark locations, will grow larger, brighter, eventually dominating the heavens. Stars will crowd the sky as 2 galaxies' worth of suns mingle overhead. New stars will form as gas clouds collide and compress. It will be spectacular, a cosmic event playing out over millions of years, visible across generations if any human descendants remain to watch. Through all this, dark matter operates quietly in the background, its gravity orchestrating the dance. The visible fireworks, stellar collisions, gas shocks, bursts of star formation are secondary effects. Dark matter's invisible influence shapes everything, the choreographer whose presence is felt but never seen. 4 billion years is almost incomprehensibly longer than Earth has existed, longer than life has flourished, longer than the sun has burned. Yet for the universe, it's merely another chapter, another turn in the endless cosmic cycle of formation, collision, merger, and renewal. Dark matter might solve the baryon asymmetry problem. In the early universe, matter and antimatter should have existed in equal amounts. When they met, they annihilated, converting to pure energy. This should have left a universe empty of matter, containing only light. Yet here, our matter exists. Antimatter is rare, and no one knows why. Perhaps dark matter's history parallels this mystery. If dark matter underwent its own matter-antimatter asymmetry, more dark matter particles than dark antiparticles, the mechanisms creating both asymmetries might be connected. Understanding one might illuminate the other. 2 mysteries sharing a common solution. This requires the universe to be more subtle than standard models assume, with new physics operating in both visible and dark sectors, creating parallel imbalances through related processes. It's beautiful theoretically, nature using the same trick twice, creating existence through carefully calibrated asymmetry in multiple domains. Testing this idea requires understanding dark matter well enough to determine whether dark antimatter exists, and, if so, in what proportions. Current experiments can't answer this. We haven't detected dark matter at all, let alone determined its matter-antimatter ratio. But future discoveries might reveal these connections, showing that the universe's deepest mysteries are intertwined. Every atom in your body exists because the universe is asymmetric, because somehow more matter than antimatter survived the Big Bang's first moments. If dark matter shares this asymmetry, then both you and the invisible halo surrounding the galaxy owe existence to the same mysterious imbalance. You're connected to dark matter, not just spatially, but historically. Products of the same primordial symmetry breaking. This thought can feel lonely or comforting, isolating or connecting, depending on your mood. Right now, as you rest, let it be comforting. You're part of a larger story, connected to everything visible and invisible. Your existence woven into the cosmic tapestry at the deepest level. You belong here, in this universe, in this moment. Dark matter could hide in higher dimensions. String theory and related frameworks suggest additional spatial dimensions might exist beyond the three we experience. These extra dimensions might be curled up small, inaccessible to normal matter, but potentially available to dark matter. If dark matter partially exists in these higher dimensions, it would explain why it barely interacts with normal matter confined to 3 dimensions. Imagine reality as a surfacer sheet of paper and normal matter as drawings on that surface, unable to leave the page. Dark matter might be able to move off the page into the surrounding 3-dimensional space, interacting with the drawings only through gravity, which extends through all dimensions. It's physically there, but mostly elsewhere, in directions we cannot point to or access. This possibility makes detection even harder. If dark matter spends most of its time in higher dimensions, only visiting our 3-dimensional space occasionally, the already rare interactions become rarer still. We'd be trying to catch visitors from another dimension, entities that drift through our reality without fully inhabiting it. Testing this requires either finding evidence for extra dimensions which particle physics experiments seek but haven't confirmed, or developing theories, making specific predictions about dark matter's higher dimensional behavior. Neither is currently possible, leaving the idea speculative, but not impossible. The universe might be far stranger than we imagine. More dimensions, more complexity, more richness than 3 spatial dimensions plus time can capture. We might be like 2-dimensional beings trying to understand a 3-dimensional universe. Our perspective limited by the dimensions we inhabit, unable to visualize or access the full reality. Dark matter reminds us of this limitation. We're blind to most of existence, sensing only a small fraction of what surrounds us. Our instruments extend our senses. Mathematics extends our intuition. But ultimately, we're finite beings attempting to comprehend potentially infinite complexity. Humility seems appropriate. So does wonder. The universe exceeds our grasp, yet we keep reaching, keep questioning, keep pushing against the boundaries of knowledge. That persistence is very human, refusing to accept ignorance, demanding explanations, seeking meaning in mystery. As your consciousness softens towards sleep, let this duality rest in your mind. You are small and the universe vast. You are ignorant and the cosmos complex. Yet you are also part of it, not separate, but integral. Your awareness, a manifestation of the universe knowing itself. These truths coexist without contradiction. Dark matter is everywhere and nowhere, everything and nothing, the majority and the mystery. Like consciousness itself, undeniably present, yet unexplained, shaping everything yet remaining elusive. The foundation we stand on while reaching toward stars. Let the paradoxes blur, let the questions dissolve. Tomorrow you can wonder again, seek again, question again. Tonight, rest in the darkness, knowing it holds you gently, invisibly, as it always has. Dark matter might have temperature gradients, just as Earth's atmosphere has warm and cool regions. The dark matter halo surrounding the Milky Way might contain temperature variations, where dark matter particles move faster or slower relative to each other. These gradients would affect how dark matter clumps, how it responds to disturbances, how it shapes the galaxy's evolution. Detecting these temperature differences requires measuring dark matter's velocity distribution in different locations, currently impossible since we can't detect dark matter particles directly. But someday, if we develop the technology, we might map the dark matter halo's thermal structure, revealing a hidden weather system operating on galactic scales, invisible storms and calm regions shaping the galaxy's gravitational landscape. Imagine dark matter jet streams flowing through the halo, regions of turbulence where ancient galaxy collisions stirred things up. Quiet zones where dark matter has remained undisturbed for billions of years. The galaxy would be alive with invisible motion, a dynamic system far more complex than the peaceful appearance of the night sky suggests. You orbit through these invisible currents without noticing. The solar system's path around the galactic center carries you through varying dark matter densities, temperatures, and flow patterns. Sometimes you swim upstream against dark matter currents, sometimes downstream. The journey takes 225 million years to complete a cosmic voyage you'll never consciously experience, but are always undertaking. Dark matter could form nuggets of strange matter. Some theoretical physicists propose that under extreme conditions, perhaps during the Big Bang or inside neutron stars, dark matter might collapse into ultra-dense nuggets, tiny concentrations of mass weighing as much as mountains compressed to the size of atoms. These nuggets would wander the galaxy like invisible bullets, their gravity so concentrated they'd create measurable effects despite their tiny size. If such nuggets exist, they might occasionally pass through Earth, potentially detectable through seismic sensors or other instruments sensitive to tiny gravitational disturbances. Experiments have searched for such events, mysterious signals that might indicate dark matter nuggets tunneling through the planet, but nothing conclusive has emerged. The idea feels like science fiction, invisible, ultra-dense objects passing through solid matter, ghostly masses defying intuition about how reality should work. Yet the universe has shown us repeatedly that reality exceeds imagination, that nature employs strategies we'd never conceive without observational guidance. Perhaps dark matter nuggets exist, perhaps they don't. The universe will reveal the truth in its own time, through careful observation and patient analysis. Science advances through accumulation of evidence, not through belief or hope. We propose ideas, test them, discard those that fail, refine those that survive. The process is slow but reliable. The South Pole Telescope maps dark matter through the cosmic microwave background. By observing how this ancient light gets slightly distorted while passing through dark matter concentrations, astronomers can map dark matter's distribution across vast regions of sky. The distortions are incredibly subtle changes in temperature of millionths of a degree, but modern instruments are sensitive enough to detect them. These maps reveal the cosmic web in unprecedented detail. Dark matter filaments spanning hundreds of millions of light-years become visible. Galaxy clusters appear as dense nodes, voids show as regions of relative absence. It's like having X-ray vision for the universe, seeing through the visible matter to the invisible scaffolding beneath. The maps match predictions from computer simulations remarkably well. The cosmic web simulations predicted before observations confirmed it actually exists, vindicating decades of theoretical work. This agreement between prediction and observation is one of science's most satisfying moments. When mathematics developed in isolation successfully describes reality, but perfect agreement doesn't exist. Small discrepancies appear, tensions between observations and models, hints that something remains unexplained. These small mismatches often prove more valuable than perfect agreement, pointing toward new physics, unexpected phenomena, deeper understanding waiting to be discovered. Dark matter research thrives on such discrepancies. Each unexplained anomaly might be the thread that, when pulled, unravels a larger mystery. Or it might be nothing measurement error, statistical fluctuation, or misunderstood systematic effects. Distinguishing real signals from noise requires patience, expertise, and a large dose of skepticism. Skepticism isn't cynicism, it's intellectual honesty, demanding extraordinary evidence for extraordinary claims, refusing to believe something just because it would be exciting if true. Good scientists cultivate this skepticism while remaining open to genuine discovery, a difficult balance requiring both critical thinking and creative imagination. Dark matter might not exist in the universe's largest voids. These cosmic deserts, regions hundreds of millions of light-years across containing few galaxies, might be so depleted of dark matter that their gravitational effects differ from dark matter-rich regions. If so, galaxies forming in voids might show different properties, different rotation curves, different stellar populations, different evolution histories. Some observations hint at this possibility. Void galaxies do appear slightly different from galaxies in dense regions. They tend to be smaller, bluer, more actively forming stars. Whether these differences trace back to dark matter distribution or other environmental factors remains unclear. Disentangling causes from effects in such complex systems is extraordinarily difficult. Voids are laboratories for studying dark matter in low-density regimes. Most dark matter research focuses on galaxies and galaxy clusters where dark matter concentrations are highest. Voids provide the opposite, extreme regions where dark matter exists but barely, where its effects are subtlest, where alternative gravity theories might show the clearest differences from dark matter predictions. Studying voids requires surveying huge volumes of space to find enough examples. Modern galaxy surveys are finally providing this data, mapping hundreds of thousands of galaxies across billions of light-years, identifying voids and studying their properties systematically. The universe's empty spaces might hold secrets that crowded regions cannot reveal. Empty space isn't truly empty. Even in the deepest voids, quantum fields fluctuate. Virtual particles momentarily exist, then vanish. Dark energy permeates everything. Emptiness is provisional, temporary, a human concept more than a physical reality. The universe abhors true vacuum. Dark matter participates in this cosmic fullness. Even spread thin across void regions, it exists, contributes gravitationally, shapes, however subtly, the evolution of structure on the largest scales. Nothing is truly isolated. Everything influences everything else through gravity's infinite reach. Gravitational waves might travel through dark matter differently than through empty space. If dark matter has any effect on spacetime's properties, even a tiny gravitational waves passing through dark matter-rich regions might travel slightly faster or slower than through dark matter-poor regions. This would create detectable timing differences in gravitational wave signals. LIGO and similar detectors haven't found such effects yet, constraining how strongly dark matter can couple to gravitational waves. This null result eliminates certain exotic dark matter theories while leaving others viable. Each non-detection teaches us something, narrowing the parameter space where dark matter can hide. Future gravitational wave observatories will be more sensitive. LISA, a space-based detector planned for launch in the 2030s, will observe gravitational waves at lower frequencies than ground-based detectors, potentially revealing dark matter effects invisible to current instruments. The universe might be whispering secrets in gravitational wave signals we haven't learned to hear yet. Listening requires patience. The first gravitational waves detected the collision of two black holes, 1.3 billion light-years away, weren't observed until 2015, a century after Einstein predicted their existence. Advanced detectors needed decades to develop theoretical understanding, decades more to mature. Great discoveries often require generational efforts. Scientists building on predecessors' work, progress measured in lifetimes rather than years. You're living through a golden age of cosmology. More has been learned about the universe in the past 50 years than in all prior human history. Satellites map the cosmic microwave background with exquisite precision. Telescopes peer back to the universe's first galaxies. Detectors catch gravitational waves and neutrinos from distant catastrophes. Supercomputers simulate cosmic evolution. The dark universe gradually reveals itself. Yet, mysteries remain. Dark matter's identity, dark energy's nature, the universe's ultimate fate. These questions persist despite tremendous progress. Perhaps they'll remain forever, partially answered. Reality's complexity exceeding our ability to fully comprehend it. Or perhaps future generations will solve these mysteries and encounter new ones we haven't imagined. Either way, the journey continues. Each generation builds on the last, knowledge accumulating, understanding deepening, the cosmic picture gradually coming into focus. You're part of this grand human project, seeking to understand the universe, to know our place in it, to push back the darkness with the light of knowledge. Metaphorical light, anyway. Dark matter ensures most of the universe remains dark, unknowable through light, accessible only through inference and mathematics. We study shadows to understand substance, measure absence to infer presence, use what we cannot see to explain what we can. Dark matter might experience friction with itself, not through electromagnetic forces. Dark matter doesn't respond to those, but through more exotic interactions. Physicists call dark photons or dark gauge bosons. These hypothetical particles would mediate forces between dark matter particles, creating drag when dark matter clumps move past each other.